So welcome everyone who is watching. Our speaker today is Professor Mohammed Hassan, and he is an assistant professor of physics and optical sciences at the University of Arizona. He has 13 years of experience in the attosecond physics and ultra-fast electron microscopy from the Max Planck Institute for Quantum Optics in Munich in Professor Ferenc Krau's group in 2013. And he joined Professor Ahmed Zavai's group at Caltech as a postdoctoral scholar through 2017. So really big shots here. And earlier in his career to generate the first optical attosecond pulse, the shortest light pulse documented in Guinness World Records. So there is, this Guinness book. And exploiting this tool, he measured the time an electron takes to respond and move. And his breakthroughs have been published in high-profile journals. And he is currently well known. The attosecond electron microscopy, Attomicroscopy, which is a camera that films the electron motion in action. So I remember some years ago, people were asking, okay, is this fact or fiction? So we're going to hear today that it's becoming less fiction and more fact, right? And use this tool to image the electron motion in solid state. And this electron imaging opens a new era in ultra-fast electron imaging and will lead to many breakthroughs and high-impact scientific achievements. Attomicroscopy imaging opens a new window to the quantum world and recently has been granted a patent for his Attomicroscopy camera. And furthermore, he has established a new methodology to sample the light field of ultra-fast laser pulses and a new methodology to measure the electronic delay response in the neutron matter. Also, he demonstrated the attosecond optical switch. So yeah, we have now switches in the attosecond domain, which is quite good, and the capability to encode data on ultra-fast laser pulses, which paves the way to establish attosecond and femtosecond optoelectronics working at the petahertz speed. Actually, if this is achieved in the future, we're going to have super fast computers and devices, and we are moving close to that. And Hassan received the International Max Planck Fellowship in 2009, the Air Force Young Investigator Award in 2019, and many prestigious awards for his Attomicroscopy project from the Gordon and Betty Neal Foundation 2018, the W.M. Keck Foundation 2019, and recently the inaugural AFSOSR Directors Research Initiative Award 2022. Moreover, he was awarded 2022 Historically Black Colleges and Universities and Minorities Serving Institutions for his institute. So he's making history, actually, a lot of us are, right? And I'm really happy to have him here today. I'm happy he accepted the invitation, and we're looking forward for his talks. And you ready to go?
Okay. So thank you so much for the Atto Fridays team.
Are you frozen? You're good.
Okay, great. I'm so happy to be with you guys, and thank you for the Atto Fridays team for the invitation. It's a pleasure to contribute. It's a great effort. Today I will talk to you about our achievement in attomicroscopy and the capability of imaging and controlling the electron motion in action. So let's start the story from the beginning. So the story starts Now we are agreed that we are in the era of imaging. Everybody has a small camera in his pocket, right? And we use this technology development in imaging to document all the events we have in life. So if we are going camping or if we are going trip, we are using these cameras to record this moment of life, either in the static mode, so we take an image, or in the live mode where we take a video to document all the event and what's happening in real time. I hope you can hear me. Can you confirm? Can you hear me?
Yes, we can hear you. Thank you.
Okay, great. So let me take you back to tell you how this whole imaging started. So this has happened exactly 1,000 years ago, uh, from where I came from in Egypt, where a very known scientist, his name Hassan ibn Haytham or Al-Hudhayn, discovered for the first time the concept of imaging. So Al-Hassan ibn Haytham also has a very famous book. It's called Book of Optics, which considered is a building block for all the lasers and optic science we have now. So if you look to this picture here, the people were passing by this room, which was a dark room. Nobody was living in this room. And they usually see through this hole, and they can see people are moving and stuff like that. So in the beginning, they thought like, oh, wow, there are ghosts inside. But he has a scientific mind. So he started to analyze what this observation, and he brings this white screen over here and they try to see what's going on. Then he figured out that he has an inverted picture of this building here on his screen through this hole. So he put the basis or explained the basis of that, and this is the basic principle of imaging. And by the way, there's in Arabic language, there's small hole which in a window which allow you to see inside what's going on. It's called camera, and it's now becomes a camera which we know now. So the basic principle of the name camera is coming from this. And this was considered the first imaging experiment in the history. And but this is for a static image. Now the question was how we can take a video or a real time image. And for that, we will come back to US. The eighth governor of California, his name is Stanford, and he was obsessed with horse racing, and he had a very fast horses, and he has a very interesting theory. He says, this horse, when he entered to the race, at a certain time moment, all his legs are off the ground. And he tried to prove his theory. So he hired the scientist, Mary Bridge, to run an imaging experiment for him to prove the theory. So they started the imaging with a slow shutter, and the picture was blaring, and he was not able to prove his theory. Then later on, he worked with Maybridge to try to see better images, and as it said, the engineer from San Francisco able to invent for him a very fast shutter for his camera with speed of half a millisecond. When he uses the shutter, he was able to take these images. You can see it here. And he combined them in the video you can see here. And this picture shows at a certain point of time, the four legs of the horse are off the ground. And he published this pioneer imaging experiment in 1982. And this also was the basic experiment or the pioneer experiment for imaging a video or imaging a moving object. What we learned from this experiment was so important. which is to image a fast object. Clearly, you have to have your camera with a shutter speed faster or equal to the speed of the moving object. And this was a very, very important experiment. We use this principle later on our ultra-fast science to image the motion in fast molecules and atoms by the time resolve technique, by freezing the time. So in the time resolve technique, we have two laser pulses, one called the bump pulse, which triggers the dynamics inside the target, and the probe pulse to be able to see these changes. So the probe pulse here in this case acts as a probe. So we measure indirectly the spectrum of the target of the probe pulse at a different instance of time as a function of the delay between the bump and probe. And as we can see, accordingly, the spectrum of the probe pulse is changing in time. Okay, so we can combine all this spectrum imaging, and we see the change in the spectrum, and from that we can retrieve back the motion of molecules and atoms. Because in this case, the shutter speed is our probe pulse. So if you have a very short pulse enough, which faster or equal to the speed of molecules and atoms, you will be able to capture it. So there are different types of motions for atoms, molecules, and electrons, and it depends on the separation in the energy state. So we can see that for atoms and molecules, they are moving in picosecond time scale, because energy separation in this case is in the order of millielectron volts. And the capability for doing time resolve and trace this dynamics or motion of atoms and molecules lead to establish the field of femtochemistry, which got a Nobel Prize in 1999 by Ahmed Jubair. So if we dig more inside the matter, inside the atoms, we'll find that the electromotion, which happens in atoms, molecules, and nanostructures. Because the energy separation between the energy state, electron energy state, is in the range of 1 electron volt or more, so the electrons is moving much faster in the time scale of few femtoseconds or attosecond time scale, and this gives a birth for 22 years ago to the field of attophysics. So for the people that don't know the speed of attosecond, so it's 10 to minus 18 of a second, or another word, 1 attosecond to 1 second is similar to 1 second to the edge of the universe. So you can imagine how fast this electromotion. I'm interested to image this electromotion because electrons is in the heart of all phenomena in nature, and I can give you some examples here. For example, we can see because of the electromotion. If we check the vision process, there are some photons enter to our eye, which is our camera in this case, and these photons is entering to the eye, go to the retina in the back of our eyes, and excite the electrons inside the molecules of the retina. So these electrons are moving inside the molecules and create a vision signal. And this vision signal is carried also through electrons through our nervous system until it reaches to the brain and form the image which we are seeing. So we are seeing the light because of the electron motion. Also, the valence electromotion is controlling the chemical reaction between the atoms inside the molecules. And for sure, the capability of imaging and controlling this valence electromotion in atoms will enable us to control the chemistry, the chemical reactions, and the chemistry. So this is also a very important example for the electron effect in our life. And finally, in solid state, most of the electronics we are seeing nowadays is based on switching on and off the electron current with nanosecond time scale. The capability for imaging and controlling the electron motion in solid state with ultra-fast laser pulses will enable us to establish a very fast electronics. And for sure, this will have a great impact in our real life if we have faster electronics and faster electronics, which will allow to transfer data and information in very fast time scale. So these are some of the examples of the importance of electromotion in our life. As I said, in 2000, beginning of the millennium, we wanted to see these electrons, to study these electrons. And this starts with pioneer work by generating the XUV pulses, which in this case will be our probe or shutter. If you remember from the experiment of the horse, that we need a shutter with the same speed or faster to be able to take images. So for electrons, it happens in attosecond time scale. We need to have an attosecond pulses. And in 2000, the field able to generate the first XUV pulses by focusing on a 4 femtosecond pulse in a gas jet to generate through higher harmonic generation to generate the X-ray or XUV pulses. This event has been highlighted in the press release of Nobel Prize in 2018. The importance of attosecond field or attosecond science, which I consider is science of tracing electrons or studying electrons. So this is so important field of science. So far, the field has established based on using two tools, the few cycle pulses to generate the XUV pulses, but we have some restriction using these tools, which is, for example, the XUV pulses has a little bit of high energy, so we can use it to trace the electrons of matter in the ionization form, and also we able to use it for nuclear systems, but not so complicated systems, because at the end we are using spectroscopic techniques, which need some simulation to be able to retrieve the electron motion. So the field called for a new tool to be able to trace the electron motion in more complex systems and in neutral systems. This tool is attosecond electron pulses, and also we can generate the attosecond laser pulses. So it's a laser, not XUV, it's a laser pulse, which has attosecond resolution. So you'll be able to trigger the dynamics using these attosecond laser pulses and see the dynamics through the attosecond electron pulses by microscopic, by the base of microscopic techniques. So you are able to image the electron motion in real time and space. So it gives you an access to the space domain as well. So this is a basic principle of the attosecond electron microscopy or attomicroscopy. I strongly believe that the capability of imaging and controlling the electron motion in real time will promise for a great breakdowns in science and technology, as I explained before. So before I start to take you to the attomicroscopy or the development trip to reach it to the attomicroscopy or the attosecond resolution inside the electron microscope, I will go a little bit back and explain for you the establishment of the ultra-fast electron microscope. This happens in 2006 in the Schwartz group. So they modified the TEM microscope, and instead of generating a continuous electron pulse, they used a UV pulse and focused it in the tip, photoemission tip, inside the microscope to generate ultra-fast electron pulses with 500 femtosecond resolution or 1 picosecond resolution. Then they come with another laser pulse to trigger the dynamics, the basic principle of time resolved measurement, as I explained before. So this laser pulse triggers the dynamics, the atomic motion or the molecular motion, and this broad pulse coming from the photocathode is probing this dynamics and take images, and we can form now a movie about the atomic and nuclear motion. So this is the ultra-fast electron microscope, and over the past 15 years, it has proven a very wide range of applications. For example, we can see the morphology and phase transition in gold nanofilm, as you can see it here, or even we can, or we used it already for visualizing the motion of dimer of nanoparticles here in a liquid cell, which happens in nanosecond time scale. Also, we use the ultrafast electron microscope to trace the motion of carbon nanofilm hit it with a laser pulse. The other alternative tool for ultrafast imaging is ultrafast electron diffraction. And this is a little bit different than the electron microscope. The electron microscope is restricted in terms of the resolution, because the electron is generated in the photocathode and travel long distance to achieve to the sample. So there are some space charge effect, which lead to a very long pulses. However, for the ultrafast electron diffraction, it's based on the same principle. So you are using UV pulses to generate electron pulses, but the ultrafast electron diffraction is more flexible. So you can change the distance between the sample and the source to reduce the space charge effect, or even to use a compression technique to generate a very short electron pulses. And it allows the imaging through the electron diffraction. One of the main advantage of using the ultrafast electron diffraction is the capability for introducing a compression scheme to generate very short electron pulses. And this is based on RF compression, so you can see the electron pulse generated from the photocathode and travel in its way to travel to the sample. We can put this RF compressor to try to deaccelerate the fast electrons and until they achieve all the electron in the wave packet in the same, almost in the same time, to generate very short electron pulses. So the best compression has been achieved so far is in the range of 160 femtosecond full wave maximum. And through this pioneer work demonstrated in 2010. There are also the capability for going in even mega electron volt electron energy, acceleration energy, which exists in SLAC. So they use this mega electron volt for studies through the diffraction, the atomic motion with a resolution of 100 or 150 femtoseconds. Similar to the ultrafast electron microscopy, the ultrafast electron diffraction also found in a wide range of application for tracing the atomic motion. So it has been used to study the ring opening in chemical reactions and the atomic motion in different systems, the melting of the aluminum, thin films, and also phase transition in vanadium dioxide. So these two tools give us the capability for tracing the atomic and nuclear motion in real time in the range between 100 femtosecond and more. So this is V-graph, or this plot show you the advancement in timber resolution both in UED, ultrafast electron diffraction, and ultrafast electron microscope from the beginning of 1985, when they started to generate an ultrafast electron pulses. So it starts at 100 picoseconds and until recently achieved the 100 femtosecond resolution. For the UEM, starting from 2006, when they started the development of this imaging tool, it starts with a nanosecond time scale, and it has been improved to reach around 500 femtoseconds. As I told you before, the electron motion happens in few femtoseconds, so in this area, and in attosecond time scale. And to be able to image the electron motion, we need to enhance the timber resolution to order of magnitude to reach the attosecond resolution both in ultrafast electron diffraction and ultrafast electron microscopy, and this can be done by generating a single isolated attosecond electron pulse, and this was the target of my research. So as I explained before, the generation of electron pulses inside the microscope is so restricted, we cannot implement any compression technique. However, in 2009, there was this nice work about the interaction between the free electrons generated inside the microscope and the laser pulse. So when the electron pulse passing through the sample inside the microscope, you see the spectrum here in black. There are no interaction happens with the photons. However, when the photons interact and couple with the electrons on a nano structure, so the photon speed is slowed down to be similar or in the range or in the same level of the speed of electrons, then the coupling happens and we see this coupling effect in the electron energy spectrum, as you can see. So some of the main electrons are gaining or losing one or more photon quanta from the laser, which means in another word, is electrons which gain electrons or lose electrons has a similar temporal profile to the laser. And in 2015, I figured out that we can use coupling between the free electrons and the laser pulse to generate shorter electron pulses inside the microscope, because we cannot control the electron temporal profile, but indeed we can generate very short laser pulses. So this is the main idea. When the electron pulses coming from the photocathode interact with the laser, the electrons gain or lose energy. And I highlighted here these electrons exist only when you have the laser, which in another word have a similar temporal profile to the laser pulses. We can use this to enhance the temporal resolution and generate shorter electron pulses and filter these electrons and use it for different imaging modes of dynamics triggered by another laser pulse. We can use direct imaging, or even we can use it for electron diffraction. The demonstration of this capability for generating a short electron pulses that break the limit of 100 femtosecond has been demonstrated. I have demonstrated in 2017 using a very short laser pulse. So as you can see, I made some modification on the ultrafast electron diffraction. Now I'm using two laser pulses in the range of 30 femtosecond. One of them to interact with the electrons and generate short electron pulses, and the other one to trigger the dynamics. So as you can see, this is an electron energy spectrogram showing here the main electrons, which has a 5 femtosecond temporal profile. Okay, and at the edges here, you can see in both sides, this is the gated electrons, which has a similar temporal profile to our gating pulse we use here in the 30 femtosecond. To demonstrate that or to characterize the temporal profile of this gated electron, we perform a cross-correlation measurement. So we have gated electrons and we use another laser pulse to gate electrons. Then we take a cross-correlation between two gated electrons in the both sides here. As you can see, this is the main temporal profile of the 500 femtosecond laser pulse, and it has a dip due to this cross-correlation measurement, which represent the gated electron temporal profile. So we measured this, we extracted this dip cross-correlation temporal profile here, and as you can see, it has a full wave maximum of 50 femtosecond, represent and a gated pulse duration of 30 femtosecond because of this cross-correlation. And to prove this capability more, we had to change the duration of the gating pulse, make it broader to 110, and see this effect in our cross-correlation measurement. And indeed, it makes the cross-correlation temporal profile longer, 175. So this demonstration showed that the capability of using laser pulses to control first the free electron pulses inside the microscope and generate very short laser pulses, which can be used, for example, to image surface plasma. This is an image of a silver nanowire, and here is the gated electrons in the both sides. So this opens the door for establish the attomicroscopy or the attosecond electron microscope. All what we need in this case is to use the half cycle laser pulse, which I have demonstrated before, to gate or slice some of the electrons from coming from the photocathode and generate in a very short electron pulses in the range of less than 1 femtosecond, then filter it out and use it to image the electron motion. We believe the attomicroscopy is a very important tool to add to the ultrafast science, and it will be similar to Rosetta Stone effect for imaging the electron dynamics in complex and quantum systems. Some of the examples we can use, we can attomicroscopy in science, for example, we can trace the charge transfer in molecules. We can try to see the chemical reactions dynamics. And finally, we can use it also to understand the electron motion in solid state, with the hope that to connect between the morphology of the solid state samples and its electronic dynamics, which will be very important for engineering and ultrafast electronics. So this is what we expected to happen in the next few years from the attomicroscopy. And yeah, so this is the first part of my talk. Now we talk about electron control. So the first part was about the electron imaging. Now we go to electron motion control. I don't play golf, but maybe you know how this nice game is played. So to control the motion of the golf ball, you have to use different drive. Depends on what you want, or the motion of this ball. You would like to have a long shot or short shot. So they are the key point here is to control the drive. And in our case, the drive of electron motion inside matter is a field, the laser field. So in this case, we need to change this drive. We need to have a control on this drive or synthesize this drive on demand. So this is the main goal, to be able to control the electron motion. For synthesize and control the generation of the electron field, we go to the light field synthesis concept, which I am showing here in this big graph. To be able to synthesize the field with attosecond resolution, we need first a coherent light source, which can generate a broadband spectrum, spans around 2 octaves. Then we divide the spectrum to different spectral channels. We control the relative phases and the relative intensities between these different spectral channels before we combine them again by superposition, coherent superposition, to generate an arbitrary waveform by controlling first the relative intensities and second the relative delays between these channels. And the most important part in this synthesis procedure is to be able to characterize the synthesized field. So the first part we satisfied by generating a broadband spectrum by focusing on a 15 femtosecond laser pulse interval at 800 nanometer. And this is a beam profile inside the holoco fiber filled with an neon gas under pressure of 3.5. And the spectrum of the enter pulse or the driver pulse here spans from 700 to 900. With that, we're able to generate a supercontinuum, which spans from 200 nanometer up to 1000 nanometer, covering more than 2 optical octaves in the visible region. Then we use this supercontinuum and we send it to our light field synthesizer device. And inside this device, we divide this broadband spectrum to 4 spectral channels. The first one in the DBUV spans from 270 to 350 nanometer, and the UV channel from 350 to 500 nanometer, the visible from 500 to 700, and the IR from 700 to 1000 nanometer. And we use a compressor, bare chip mirrors compressor, consists of 6 mirrors, to compress each individual spectral channel close to the Fourier limit. Then we combine all these channels again. It's a sophisticated interferometer in another word, to form as a synthesized field at the exit. This is how the synthesizer field, synthesizer device looks like in the real life, and you can see a little bit of the color from different spectral channels. Even highlighted in Nature Photonics as a new tool on our ultrafast science field. So this is how it's a small video to show you how this synthesizer works. So you can see this broadband spectrum is divided to different spectral channels, as you can see here, compressed by the compressor, chip mirror compressor. before they combine again at the exit of the synthesizer to form the synthesized field. If you can look here, we have different very high precise piezo stages to control the relative delays between the channels, and also we have the capability to control the relative impedances between these channels. So this is the device we use to control the field or to synthesize the field with attosecond resolution. But however, we need the most important step in this process, which is light field sampling. Light field sampling is not important only for light field synthesis, but also if we're able to provide a new methodology for light field sampling, will allow us to make a direct connection between the dynamics we are seeing in any times of measurement and the driver field, which will allow us to extract more physics from the times of measurement. For that, indeed, it was a very robust technique before, like the attosecond streaking and that clock to retrieve or to sample the electric field of laser pulses. However, this is a very costly technique and requires a sophisticated high harmonic generation and XUV streaking setup. But we find another way by exploiting the strong field interaction with dielectric systems to retrieve the field sampling. The main idea is the electrons in the dielectric is excited from the conduction band to the valence band, and then it's moving or it's changing momentum with the driver field in the conduction band, and the electrons move following the shape of the field. And this changes the optical properties of the dielectric and changes the reflectivity. So the capability here to retrieve or to trace the reflectivity modulation will give us a direct access to the field shape of the driver pulse. Our setup for doing the light field sampling is shown here and is very simple. We come with the input beam or the input pulse from the light field synthesizer. We have a mask here to generate two pulses with the same waveform. So this mask has two holes. One is very small to generate the weak field pulse or the probe pulse in this case, and a big hole to generate the strong pulse or the bump pulse. We focus the bump and probe pulses by using these two D-shaped mirrors. One of them is mounted on a delay stage, and we focus it on our dielectric system. In this case, is silicon dioxide. Then we take the reflected probe pulse and we filter it out, and we measure the spectrum using a normal optical spectrometer, and we measure the change in the reflectivity or the change in the intensity of the measured probe spectrum as a function of the delay between the bump and the probe. So in a sense, the bump is changing the reflectivity, and the probe can trace this reflectivity change. So to prove that, we start with a 6.5 femtosecond pulses characterized by the typical frog technique. This is just a demonstration of the capability of this light field synthesis methodology. We perform the reflectivity modulation experiment. So we measure the reflectivity of the probe pulse, and we take the integration of this probe spectrum at each individual spectrum. So each point here represents the integration of the probe spectrum as a function of the delay between bump and probe, and we measure this trace of changing in the reflectivity of the probe pulse from silicon dioxide, and this represents the effective potential of the field. We can retrieve the electric field, and from this electric field we can get the temperature profile of the pulse, which turned out to be very similar to what we measured from the frog. So this is an proof of principle experiment. And the question was, is the silicon oxide is the only dielectric system can be used? For that, we tested also the calcium fluoride, and this is a reflectivity modulation using the same bump pulse. And this is a retrieved field. You can see the similarity between the retrieved field in both cases, and indeed the temperature profile was similar to the frog. So this is an approved principle that we can use this new methodology of reflectivity modulation of dielectric and strong field to characterize or to sample the light field of pulses. So in this case, we complete the requirement for on-demand light field synthesis. We use our synthesizer. We have an unknown field. We don't know how this field looks like. We go to the all-optical field sampling experiment, which I just showed to you. Then we able to measure a field. From this measuring field and with a small analysis, doing Fourier analysis, we can retrieve the relative delays between the synthesizer channels. Then we can send this to a certain algorithm to modify the relative delays to generate the expected or the desired field in this case. Then we send this new relative delays as a signal inside the synthesizer to move the delay stages. When we move the delay stages, we generate a new field and we go again to the all-optical field sampling to see how this comparable, the new generated field comparable to the expected field. This is what we measure, and this is the expected field. So after 2-3 iterations, we can reach to the demand field, or the field which we wanted to later on use it for electron control measurement. This work, if you would like to hear more or to understand more about the details of work, I will refer you to this recent publication from my group, Attosecond light field synthesis. To demonstrate the capability for sampling the field with very high resolution both in time and spectrum, we used a synthesized field and we sample it, as you can see it here, by tracing the reflectivity modulation, and we track the electric field. And this is given at a certain relative delay between the 4 channels. You can look here to the relative internesses between the half-cycle pulses, because it's very important. Then when we delay one of the channels, which is the UV channel, by -2 femtosecond, we generate a new synthesized field here. And as you can see, this changes the relative internesses between the half-cycle in the same pulse. This is what we measured, and this is what we expected. So it's at least in the main half cycles of the pulses, they are in a great agreement between both of them, which demonstrates the capability of our all-optical light field sampling to trace the attosecond resolution and change in the field. If we go one step further to see if changing the high frequencies, which is DBUV pulses, will be able also to resolve it by our all-optical field sampling technique. We generate this waveform by delaying a DBUV pulse by -2 femtosecond, and as you can see, another change happened here in the relative delay, sorry. And this is in the red, the measured one, and in the black dot is the expected field. So this also demonstrates the capability for resolve the very high frequencies in our waveforms. So at this point, we are so confident about the capability of our all-optical light field sampling technique to resolve the attosecond timbre resolution and the high frequency spectral resolution in our waveforms. This work is demonstrated also in this publication. If you would like to know more about the all-optical light field sampling and also the capability for controlling the electromotion in dielectric system. So to do that, we synthesize different waveforms and we trace excitation. So in black here is the electron excitation inside the dielectric, and this is the electric field we use for that. So as you can see here, we confine all the excited electrons to happen in a very short time scale, 400 attoseconds. And by changing the waveform, we can change in time the event where the maximum excitation of the electrons happens in 2-time instants separated by 0.9 femtoseconds. And we can control this excitation, maximum excitation of electrons by using different waveforms. And we can change the separation in time to be 2.7. We can have this maximum excitation happens at 3-time instants separated by 0.9 or even 4-time instance. So this is opens the door. This capability of electron motion control is the dielectric opens the door for using it for optical switching. However, in the last 3 months, IBM demonstrated the capability of having 8 different laser frequencies on a small chip. And this is a basic principle of the synthesizer. So this opens the door for making the synthesizer and all this optical switching and data encoding on the small chips, because the technology is catching up here. So another possibility or another unique advantage of using this reflectivity modulation measurement is that we can trace the delay response of the material based on measuring the reflectivity modulation and different intensities. So in this setup, or in this experiment, we are measuring the reflectivity modulation, similar to what I showed you before. However, we use here a neutral density wheel, so we can change the intensity of the incoming beam without changing anything else in the experiment, and trace the reflectivity modulation. This also work is in more detail if you would like to read about it in the publication. So, for example, we measure the reflectivity modulation in silicon dioxide using a 10 femtosecond laser pulses. And if we focus on a certain window in time, we can see that this is a reflectivity modulation at a certain intensities. By increasing this intensity, we observe a phase shift in the order of few hundred attoseconds. And when we increase more the intensity, we see the shift increases. And we attribute this shift due to the electronic delay response inside the material. And to investigate this more, we have done this experiment using a short laser pulse, but in different intensities, range from 0.35 10 to 13 to 1.3 10 to 13, just before the damage threshold of the silicon dioxide. As you can see, by increasing the intensity, you see we are marking here this field peak, and we try to trace the change of this field peak phase as a function of the intensity. This is what I show you here. And as you can see, it has a linear relation. We could think about an exponential relation. This is what we expected, but I think the delay response here happens due to, for example, the Stark shift, which is linearly proportional to the intensity of the driver field. And we have repeated this measurement also in calcium fluoride. We see the same behavior. And by extrapolation, you can determine the exact delay response of the electrons to be excited from the conduction band to the valence band inside the dielectric systems. And as you can see, there's different slopes between the delay response in silicon dioxide and calcium fluoride, which is different, makes sense because different energy gap in both cases. So at this point, I would like to thank the people they have done this measurement in my team, Dandan Hawi, Hussein, and Yahya. And also, I would like to thank our collaborators from different institutions and our funding agencies. And also, I know you have a very broad band of audience from entire the world. And I have an opening in my group. If you are interested, you can contact me on my email address here if you would like to join to our team. Thank you so much.
So thank you so much for this really nice talk. Other questions, comments, I can see they're already coming. And I'll also do something because we're very proud of having an international audience here from everywhere. So we're launching a poll. And we would like to know where you are joining from today. And while we wait for it, let's have a look at the questions. So we have 2 from Matthias Kubel. Hi, Mohammed. Very nice results. On slide 44, it seems the reflectivity for positive delays is larger than for negative delays. What is the reason for that? Is the laser pulse creating carriers in the conduction band?
45 or 44, he said.
Yeah, 44.
44,
Yeah.
okay.
Hi.
Yeah, this one. This one?
No, this one is 43. Next one. Yeah, this one.
This one, yeah. What's the question again?
Yeah, so if you compare the reflectivity for positive delays, but after the pulse is gone, or
Yes,
almost
yes,
gone, right?
yes,
Then the
yes, yes.
reflectivity is higher than in the beginning.
Well,
So the question is, why is that?
Yeah, so it depends on the driver field. You know that very well that there are some remaining electrons inside the, there are some remaining electrons inside the conduction band. So this is what you see here, a little bit more reflectivity after the pulse is gone. But however, in the analysis, if you subtract the background, this will give you the nice electric field or sample over the field here. Indeed, to have a much accurate measurement, you can do this in a very lower intensity. So you ensure that you don't have a lot of carriers in the conduction band after the field is gone, which is proven also in which measurement? Yeah, the measurement before, as you can see it here, is clean because we learn the process and we advance the process by measuring this at moderate intensities, way in the middle between the beginning of seeing the signal and the threshold, damage threshold of the material. So when you do that, you will reach this nice reflectivity modulation, which you can see it here, which doesn't show that. So.
Okay, thank you.
So clear. Are there further questions?
Yeah, the
Hello.
second question, right?
Yeah, this is only the first. Very good. Because your second question was about
the Matthias. Yeah.
Yes.
Yeah. So this refers to the last thing you showed.
Yeah.
Yeah, these yes. Yeah, so this delay dependence there. Oh, sorry, this intensity dependent shift.
Right. Yeah.
Right. How is this different from the nonlinear refractive index?
Nonlinear diffractive index.
Yeah. So you have some N2, and this also causes some delay.
This is true. I have to agree with that. That the main reason of the delay response we didn't have investigated carefully and in more details yet. However, what I'm showing here is the capability for tracing this delay response. Is it coming from Stark shift? Is it coming from the nonlinear process? Is it the time it takes from the electron to be excited from the conduction band to the valence band? Indeed, this needs a very intensive theoretical investigation, and we are working on that.
Okay.
Okay. Further questions? So let me end this poll. As you can see, you have a lot of people joining from Europe, and we have from Asia, which is the second cohort. We have people also from US and Canada and from Latin America. So you can see we have quite a few continents represented here today in our audience. So we are really pleased to see that we have people pretty much from everywhere. And we also make an announcement that now we have been asking the speakers for bonus material. So you can be sure that there is something here in the talk that is going to be removed when it goes to YouTube. I mean, we'll keep on posting on YouTube, and we're very thankful for everybody's participation and support for the channel. And we think this is also important to keep the Atto Fridays inclusive. But having said that, it's also important, and I would like to thank everybody who has joined today for supporting our speakers and showing up live. An important part of the seminar series is live discussion, and also to show support for those who take their time and come here to talk to us. Are there further questions, comments? People quiet. You will have the opportunity to ask more questions once we go offline, because I know not everybody likes to be on the internet where all your questions are displayed. And you have this opportunity. If this is your case, just hang in there. And we're going to stop the transmission soon. We are online, so I cannot offer you a coffee break. But I know that a lot of people are on YouTube today, and we thank all of those people watching. We thank you so much for your attention and for taking your time to support the Atto Fridays. We're going to stop the transmission soon. So take care of yourselves. If you want to talk,